Vulcan is a data product that's been in production for now almost over 20 years in my group. It estimates fossil fuel CO2 all across the United States. It's built from sort of a bottom-up engineering style approach, mining 20 to 30 different data sets, federal, local, all sorts of data, but its real aim is to follow fuel throughout the US economy to the point of combustion. We now create this data product running from 2010 to 2021. We're about to push out 2022. The time resolution is hourly, and the spatial resolution is a mixture of points, lines, and polygons. Polygons being the most limiting resolution, which are now down to about a US Census block, or about a city block in the United States. So very finely resolved in both space and time. Now, the first thing to look at when examining cities in the United States is this idea of the urban share. You hear this number all the time, that cities account for roughly 70% of greenhouse gas emissions globally. And that number actually rests on very limited evidence. It's a fairly hand-waving number, so it's worth looking at Vulcan to see if we can estimate what the urban share is in the United States, if it's consistent with that rough estimate. So doing this using two different definitions of cities. Of course, there are many definitions of cities. I'm going to use two. One is called incorporated places, which is essentially the administrative or governance boundary of the city. And the other is combined statistical areas, which are really more of that expansive metropolitan urbanized area concept, where you're looking at all the urban entities that are socially or economically linked together and calling that a single urban entity. Now, in the case of incorporated places, limit this to the top 4,000 cities in the United States. There's about 20,000 governance boundaries in the US. We're going to limit that to about 4,000, which is places with population over about 10,000. And the combined statistical areas, obviously, they're much, much larger. There's only 172 of those entities in the United States. And here's a map of what this looks like. On the left are the incorporated places, obviously much, much smaller. And on the right, these combined statistical areas, much, much larger. And for a lot of the analysis I'll show here, I'm really going to emphasize the combined statistical areas since they tend to be more relevant to the CO2 analysis I'm doing. I'm going to use two different summative metrics: total emissions, which includes basically everything, all fuel combusted within an urban area, and then what I'm calling an urban sum, which is the sum of the residential, commercial, and on-road sectors. And I do that because those sectors are really intrinsically related to the population within a city. So they're leaving out things like power plants and industry, which often are artifactually inside a city, but then often also not related to the population within the city. So we try to limit that to this very relevant urban sum. I'll use the phrase FFCO2 to refer to fossil fuel CO2, so there's no biogenic exchange in these estimates here. And this looks at scope 1 only. So this is just the emissions arising from a piece of geography that we're examining, not the supply chain emissions or even scope 2 electricity emissions. Okay, so when we look at these two different definitions for incorporated places, the urban share, when you're looking at total emissions, is 34.4%. If you look at that urban sum share, just those three sectors, it increases to about 50% of the US total. When we look at the combined statistical areas, that changes dramatically. No surprise, the bigger, this is what you would expect, they rise to, for total emissions, 63.7%, and for the urban sum, 76.1%. So bracketing that 70% number that we were questioning at the outset. Now you can look at this in a little more detail. You can start to break this down both by sector and start to look over time and look at what the share looks like. This is a busy plot, but the upper part, these dashed lines, those are all the definitions of the combined statistical area, right? And the solid lines are these incorporated places. And again, you expect all of those CSA urban shares to be higher than the incorporated places, but you also see a few other things. Convergence of the sectors when you're looking at the combined statistical areas. And that's because as you build out, or as you widen your definition of an urban area, you're mostly picking up residential and on-road emissions. The suburban areas that are outside your urban core. So you expect that convergence. You also see a fair amount of interannual variability in mainly the commercial and residential sector. And if you look at, unfortunately you can't see it on this plot, I'm really sorry because it was too faint, but I plotted the US annual mean temperature here, and it's essentially inversely related to the interannual variability of the urban share, which essentially meaning that when it's warm, heating emissions go down, but interestingly enough, it affects the share of emissions, not just the absolute. The other thing you see is the two solid dotted black and solid line of the urban sum. You see this dip in the year 2020 only in the on-road sector mainly, and that's really an effect due to COVID, something you know about fairly well. So you can also line up all the cities from largest to smallest in the United States. And by the way, the top 50 US cities are still the number 3 emitter. If you look at countries on the planet, top 50 cities would be number 3 in the United States, behind the US and China. Dominated by the on-road sector, but if you look at the cumulative population and cumulative emissions, they don't go in lockstep with one another, right? You actually sum up population faster than you sum up emissions. That's interesting because it starts to imply something about scaling relationships across urban sites. And indeed, if one uses an analogy analogy to allometric scaling in biology, where for about 40 years people have looked at this idea that there's a relationship between the metabolic rate of an organism and its size, and that relationship is a simple power function. You can apply this to CO2 in the notion that CO2 is like a metabolic rate of a city. And the nice thing about power functions is that they're easily linearized with log normal transformation. So you can do that here, and the regression coefficient, which is effectively the power function coefficient, if it's greater than 1, you have superlinear scaling. If it's less than 1, sublinear scaling. Superlinear scaling means that 1% increase in population leads to a greater than 1% increase in CO2, and vice versa. Now, people have looked at scaling relationships in cities. A lot of this work was done by Louis Bettencourt at Santa Fe Institute, Los Alamos Santa Fe Institute. He looked at a whole variety of urban activity metrics compared to population and examined all of these scaling relationships. He did not look at CO2, but a couple of studies since the original work by Louis looked at CO2. In fact, parenthetically, they both used Vulcan data as the underlying data set to do this examination. But I would argue they were using a much older, coarser version of Vulcan, which I considered actually insufficient to do this type of work. But those studies came to the conclusion that either cities scaled super linearly, that is, a 1% increase in population led to a 1.38% increase in CO2 in the top study. And then another study actually came to the conclusion that they scaled perfectly linearly. So it's worth, with the latest Vulcan version up, which much higher resolution, many more years of data, whether that relationship still holds or not. And the underlying question we're trying to answer is bigger better? Are there economies of scale associated with city size vis-a-vis greenhouse gas emissions? Very important question, because it would suggest that there may be some efficiencies to be gained or not. So when we look at the CSA definition, and again, I'm going to focus on that one here, what we find, in contrary to previous studies, is that there's consistent sublinear scaling across the U.S. urban landscape. And I put the scaling coefficient values both by sector and both associated with the two sums of emissions in the top line of this table, and then the standard error of that regression coefficient in the second row, just to show that they are always statistically different from 1 in this case. But in addition to being broadly sublinear, it looks like the sublinearity is intensifying over time. Because we can run this analysis on every single year of our time series. In this case, we had to start in 2013 because we did not have urban populations codified in the same way prior to 2013. But from 2013 to 2021, we see a pretty decided decline in the scaling coefficients across the board. So it looks like, in this case, bigger is better, and it's increasingly so. over time. Now, it's tempting to break the U.S. up into east versus west. And there's lots of reasons for that. That historically, there's this notion that the Western United States, more recently populated, tends to have greater urban sprawl as opposed to eastern cities. That's not always technically true, but that's certainly a notion that is worth testing against these scaling relationships. And what we find is that it doesn't appear to be the case that actually Western cities are actually more sublinear in their scaling than eastern cities, but admittedly, the standard error on these coefficients is pretty high. And because CSAs are so large and you have so few of them, that sort of lower end makes it such that the standard errors really beg the question of whether or not you really can separate east from west. Now, this clearly is an area in which we're going to be doing a lot more work in terms of cleaning up the data, adjusting it for heating degree days, and a few other things that might make the data a little more consistent and lower the standard errors on these coefficients. So, to conclude, preliminary analysis shows that the urban share is, of course, sensitive to the definition of what is urban. In this case, I simply use two that kind of bracket the wide range of urban definitions, but in the case of administrative boundaries, the urban share is relatively small, nowhere near the 70% that you hear about in just about every paper on urban greenhouse gas emissions. But that larger economy connected definition tends to bracket the 70%. Certainly viable number for what the urban share is. Of the three urban sectors, Long Road is the largest consistently, shows a COVID response. Again, things we already knew, but it's good to confirm that in the urban share data. And then this question of is bigger better, that we're finding, contrary to previous studies, that there are economies of scale in US cities as regards CO2 greenhouse gas emissions. We see sublinear scaling across the board, and that sublinear scaling looks to be increasing as time goes on. When you compare east versus west, even though the west gives some slightly counterintuitive results, unfortunately the errors are too high to really be conclusive about that. So with that, I'll thank you. Note that we have lots of postdoc openings in my group if any of you are interested in a postdoc, and thank funders, NASA, NIST, NSF, and the DOE funding development work for the last couple decades. Thank you.
Thanks, Kevin. We've got questions for Kevin.
Not only do people talk about 70%, they often show relationships which are not based upon sheer population or population density. The argument is that compact is better. Have you rearranged your data to look and remove the influence of physical size of the defined metropolitan area?
Yeah, not yet. That's definitely something to do. Because clearly, there's probably strong density dependence. That could be what's underlying a lot of this. Although I would argue, in addition to density dependence, this is probably infrastructurally related as well. There's clearly economies of scale in infrastructure, or one would hope there are. That's why, again, the west versus east was a little disappointing, because you would have expected more public transport in the eastern United States versus the west, which tends to be carbon intensive. We don't quite see that, but I think those are things absolutely worth testing.
More questions for Kevin? Okay, I'm going to ask a question.
Sure.
I think maybe the last graph you showed where you were looking at that those sublinear numbers by year, and it looked like they were dropping quite low in 2020 and 2021. And I was wondering if you think that that's a COVID response related to people not commuting as much or something like that?
I mean, it could be. And remember that what the scaling relationship, in some ways is trading space for time, because it's really looking at an instance in time across the size gradation of cities. It really isn't examining a temporal relationship. We're able to, of course, run that spatial scaling relationship on each year and see some temporal dynamics. But, whether or not in COVID there was something that was size dependent, that's the real question, was there something going on in bigger cities consistently that was different from smaller cities. One could argue, and the reason why you probably see it in the on-road, in the urban share, is that in smaller places there was probably less of a reduction in driving, that there probably was a bigger effect in larger cities, both because of legitimate health concerns with higher density places versus lower density places. I imagine in the United States there was probably also a political effect here when you go from large urban areas to less urban, more rural places. There definitely was a political layer. So probably both of those things are occurring and could very well be feeding into the scaling pressure. Whether or not it returns now as we sort of exit this period of time, we'll see.
Thank you. So we have about 15 minutes to get into the session for